Welcome to this video and sampling distributions. By the end of this video, you should be able to use a sampling distribution of a statistic to evaluate a claim about a parameter. All right, so our scenario today is building off of yesterday's. Yesterday, I gave you 4 test scores, and then we created a sampling distribution from that. This time, however, I had 90 test scores. And we're going to be taking samples of 5 out of this 90 test score. So I'm going to run you through what I got when I ran my samples, and I'll compile some data for you. But I wanted you to understand where the numbers are coming from. So we have these 90 test scores. I'm going to use my random number generator to generate a number which will tell me which scores I'm going to use for each sample. All right, so in my first sample, I got a score of 72, 89, 74, 91, and 85. When I calculated out the mean, I got a sample mean of 82.2. All right, and then I did this, so I repeated the same process. I picked 5 scores, found the mean. I'm going to get 5 more scores that I drew. 72 and 52, and when I calculated the mean, I got 73. And let me give you the other 2 sets. I want you to go ahead and calculate the mean and then the means for them and come back. So 76, 83, 85, 70, and 40. And then 85, 91, 74, 87, and 93. So go ahead and calculate those and come on back. All right, so when I calculated these scores, the means, I got a 71 and an 86 here. And I've gone ahead and made a dot plot for you of a sampling of some of our data because we had over 150 dots on our dot plot. So I didn't want to overwhelm you. So this is kind of an abbreviated version of our sampling distribution of the mean, the sample mean, because that's what we found. And so scale it back just a little bit more so you can see it. Go ahead and pause the video and copy this down and then come back when you're done. All right, so I want to remind you, each of these dots is a sample mean. Every single one of them. It doesn't matter which one you pick. They are all a sample mean. Okay, and they all represent one sample of 5 students. Okay, so each dot represents a random sample of 5 students and with and their mean. So we did a random sample of 5 students. And it's the mean calculated test score. All right, so we did a random sample, so we're hoping we had an unbiased estimator here. So let's go with the idea that we have used an unbiased estimator. Take a look at this distribution, and I want you to guess what you think the true mean is here. Go ahead and pause the video, take a minute, think about it, challenge yourself, see how close you think it's going to be. All right, let's see how you did. So in our test scores, looking here, everything should center around a particular area. I don't know what you guessed, but I'm going to tell you that the population mean, the actual mean of all of these test scores was 82.1. So 82 just right here. That was the mean of our sampling. So that should it's the mean of the population, so it should also be the mean of the sampling distribution. Because remember, if you have an unbiased estimator, which hopefully we had because we used our random number generator, the mean of the sampling distribution equals your parameter. Okay? And so I would just want to keep bringing that idea back, as it's going to center around the true population mean. Normally you don't know what the population mean is, and so you're using the sampling distribution to estimate it, and if you have an unbiased estimator, they should match. That's the whole point of the foundation of what we're trying to lay down here. So let's take a look at number 4. So a sampling distribution shows the mean calculated from all possible samples of size 5 from the population. Is the above dot plot a sampling distribution? No, we did not do all possible combinations of 5. And here's why. So let me show you on my calculator. We did a sample size of 5 and we had 90 total tests, so 90 tests. Okay, I'm going to do a combination because the order doesn't matter here. So we had 90 tests and we chose a sample size of 5 for each one. So we would have had a dot plot with 43,949,268 dots on it. And so this isn't a true sampling distribution. It's an approximation of one, but that's what we're going to use for our purposes. Okay, so here on number 4, your answer is no. We didn't take all possible samples. Because here's our reasoning. We had 90 tests with a sample size of 5. So we had 43,949,268 possible samples. That's why we didn't do it. That'd be a big sheet of paper. Okay. So this isn't a true sampling distribution, but it's an approximation of one. Now down here, I didn't finish. This should say Woodstock High School all the way through. These should say Woodstock. So if we took a random sample of 5 tests at Woodstock High School and got a mean of 68, is this convincing evidence that Woodstock students did worse than the students in our school, or is it possible Woodstock has the same average? So I want to go back up over here. 68 is what the Woodstock average they got in one sample when they did theirs the same way we did ours, of a random sample of 5 tests. So if we look at our distribution, 68 or more extreme occurs right here. There is only one value that is that extreme based on this sampling distribution. There are 30 dots here, so we got 1 out of 30 that matches their number. Okay, and so that gives us 3%. Remember that the number that we're always kind of comparing to for is 5%. This is less than 5% chance of this happening just by chance. So we would, I would start to think something else is going on. This is a really unusual result that they got, even though we got 1, but it's 1 out of 30. And if we kept going, you know, most of the numbers are going to be over here, and there's going to be less over here. So is there convincing evidence that the Woodstock students did worse than the students at Etowah? Yes, there is. So if Woodstock had the same average, it would be very unlikely and we got 3%, so I'm going to use that as my evidence of what I mean by very unlikely, to get a sample mean of 68 or lower. So their results, 68, would be really unusual. Now, if they had gotten a result of 78, well, we might be in better, because there's 1, 2, 3, 4, 5, 6 out of the 30. So that would be a lot better opportunity. So if we did 6 divided by 30, that's a 20% chance of that happening just by chance. So that wouldn't be unusual at all. But they had an unusually low result in their sample. So we're starting to think maybe they don't actually have the same average as us. All right, so let's summarize this down. Go ahead and flip on over to the back side. All right, so evaluating a claim is one of the major topics of this semester. Okay, and that's what we just did. We really evaluated the claim of Woodstock, whether or not they had the same test average for Chapter 6 as we did. So evaluating a claim, when you do this, you always want to assume that the claim is true. And you're looking for evidence against this claim. Okay, you're going to assume the claim is true. And just like we did on the front, we created a simulated sampling distribution. Okay, and then you want to use that distribution to find the percent chance of getting the observed result. Okay, so we're going to take this information. We're going to assume the claim is true. We are going to create a sampling distribution, or oftentimes the sampling distribution will be given to you. And then we're going to find the percent chance of getting the observed result. So we have to assume the claim is true. Here's our sampling distribution. So whatever the claim is, you're going to mark it off. So maybe the claim for this one occurred here. So because it's on the upper end, I want to know that far or more extreme. On our example we did on the other side, it was all the way on the other end. So we went for that far or more extreme. So it's always more extreme from the center. Okay, so if your claim is on the bottom end, you're going to go to the left to the wings of your distribution. If it's on the right, you're going to go up into the wings. Okay, and so remember, all of these dots are what's actually happened, and I want to know the percent of the dots that fall into that region. Okay, and so then we got to find the percent. If you have a less than 5% chance result, that means you have convincing evidence against the claim. So in the Woodstock, what they're really doing is they were claiming to have the same test average as us, but they had a sample result of 68. So if they actually have the same test average as Etowah, there's only a 3% chance of getting a mean sample with a 68. So that's why we felt there is evidence against their claim that they have the same average. We think something else is going on. Okay, if your result is greater than a 5% chance, then there is no convincing evidence. against the claim. Against the claim. All right. So this is the very basis. As we move forward, eventually we'll be writing hypotheses and testing which hypothesis do we think? Do we find, for the claim, or did we find for the alternative of whatever the claim could be? So here we have a scenario in our Check Our Understanding about pennies made prior to 1982. Those pennies were made of 95% copper. Because of the copper content, these pennies are worth about 2 cents each. Pennies made after 1982 are only 2.5% copper. So Jenna reads online that 13.2% of pennies in circulation are pre-1982 copper pennies. Jenna has a large container of pennies at home, and she selects a random sample of 50 pennies from the container and finds that 11 of the pre-1982 are pre-1982 copper pennies. Does this provide convincing evidence that the proportion of pennies in her container that are pre-1982 copper pennies is greater than 0.132? So here we want to identify the population, the parameter, the sample, and the statistic. So the population here are all the pennies in the jar. Okay, and your sample, she took a sample of 50 pennies. So now I want you to remember, a parameter is a number that describes a population. So when we look through here, the number that describes the population of pre-1982 pennies is at 0.132. So your parameter, and this is a proportion, so I'm going to use P, is 0.132. Okay, and your statistic, a statistic is a number that it represents a sample. It describes a sample, and we use that symbol P hat for that. So she took a sample of 50 pennies. Of those 50 pennies, 11 of them were pre-1982 pennies. So we have a sample proportion of 0.22. Okay, so does Jenna have some evidence that more than 13.2% of her pennies are pre-1982 copper pennies? Yes, she does. Because she had 22% in her sample. She had 22%. And that is greater than 13.2%. Okay, so she has some evidence. All right, so there's two explanations, and this is our basis for when we are eventually writing our hypotheses as we're moving forward. There's two explanations for what this could be. One is she just got lucky. She got a lucky sample that is unusually high. Okay, and we know it can happen. It's just how likely is it to happen? That's what it's coming down to. So she either got lucky, or her percent is actually greater than 13.2. Okay, so these would be like our hypotheses. She's claiming more. So she either got more purely by chance, or she actually does have more. Okay, those are really the two ideas behind here. So what I want you to do is I want you to stop the video, and I want you to answer 4, 5, and 6 on your own. They did the sampling distribution for you. So this is similar to what we did on the front. Try these answers and come back and check. All right, so we use technology to simulate 100 simple random samples of size 50 from a population of pennies, in which 13.2% are pre-1982 copper pennies. Okay, so we're assuming the claim is true there and going with that 13.2%. This dot plot shows the sampling distribution. Okay, so there is one dot graph at 0.22. Okay, and explain what the dot represents. The dot represents one sample of 50 pennies, which had 22% copper pennies. Okay, so you always have to understand what each of the dots represent. They all represent the same idea in their respective percentages. Okay, they're all one sample of 50, and then they're placed over the percent that they had. Okay, so assuming that 13.2% of the pennies in circulation are pre-1982 copper pennies, is it surprising to randomly select 50 pennies in which the probability 11 out of 50 or 22% or greater? So 22% or greater. So we're talking about here. So we got 1, 2, 3, 4 out of the 100, which is only 4%. That's less than the 5%. So yes, it is surprising. And I give my justification because only 4 of the samples had 22% or greater. And then based on our previous answer, is there convincing evidence that more than 13.2% of pennies in Jenna's container are pre-1982? Yes, because there was only a 4% chance. And we said up here, if it's less than 5%, we have convincing evidence against the claim of 13.2%. So assuming the claim is true, it is unlikely to get a sample with that many pennies. So we actually have evidence here that there's something else going on, that she has a different proportion than 13.2%. Hopefully that was helpful. Let me know if you have any questions. See you in class.